Well, hello everyone, Maple Structure here, and in today's video I'm gonna show you how to analyze a fixed cantilever beam with simply distributed load along the entire length. Let's get started. Initially, let's take a look at the beam. It's 6 meters length and it's loaded with distributed load with value of 15 kilonewtons per meter. No matter what a cross-section is, we will pay attention on it in next videos. Now, let's focus on shear force and bending moment diagrams. To plot those diagrams, we have to find values of shear forces all along the beam and bending moments as well. To do this, let's use the method of sections. Alright. This beam is way simpler and faster to analyze in comparison with something like simply supported beam with uniformly distributed load, just because we don't have to figure out support reactions here. But if we use the method of sections, we are able to use only the part of the beam without fixed support, so in this particular case, we'll focus on the right part. The core of this method is pretty simple actually. If we cut our beam somewhere and focus on a chosen part, we must replace the removed part with internal force vectors. As our system is in equilibrium, the internal force vectors must keep the system in equilibrium as well as the removed part did. So before we start applying this method, let's introduce the x and y axis like I did here, or any way you want. The main rule, these axes shouldn't make our problem more complicated, so we don't need to introduce them rotated if our system is straight. Keep it in mind. Okay, now let's cut our beam here, or anywhere you like, it doesn't matter, and let's take a look at the isolated right part. First, I suggest to replace the distributed load with its equivalent concentrated load by multiplying the load intensity and beam length. This force is concentrated right in the center of the isolated part, so it will be easy to figure out the arm of this force. Well, our beam is bending. When a structure bends, it tries to resist, creating internal force vectors, shear force and bending moment. By using the side convention I mentioned in my previous video, we used standard directions of those vectors. Shear force is directed upwards and bending moment is directed by clockwise. Alright, let's begin with shear force determination. We have to sum all the vertical forces along the y-axis, taking their sign into account. So what does this x mean for us? As I mentioned before, we can cut our beam anywhere, but we do not pay attention on an isolated part length and consider its length equals just x. Then we can take into consideration some values of x named boundary conditions just to plot the final shear force diagram. So we see our equation for shear force is linear with respect to x. So the math tells us we should pick at least 2 points to define the diagram shape. And I suggest to pick 2 boundary points where x equals 0, it's the right bound, and where x equals 6 meters, it's the left bound. And then we can simply connect those 2 points and define shear force diagram. Next, let's figure out the bending moment. Consider the left bound of the isolated part is the point A. Now we should sum all the moments about this point and define a bending equation. As you can see on the screen, the equation is quadratic, so the shape of the diagram is parabolic. For us, it means we have to pick 2 or even 3 points to plot the final diagram. As we did with the shear force, I suggest pick 2 boundary conditions, the left bound and the right bound, and as you can see, there are no difficulties with it. So no extra words, you can see those diagrams on your screen. And on that positive note, I'll wrap things up. If you have any questions left, I'll be happy to answer them in the comments below. That was Maple Structure. Peace.